Good morning, everyone. Just a reminder to anyone who might have a laptop in the audience, make sure it's muted if you are logged on to the session. Thank you. All right, welcome to our 10 o'clock briefing of Jovian moons and comet tails, the latest science from NASA's Juno mission to Jupiter. I'm Liza Lester from AGU. This is just a quick note on the run of program before I turn this over to our four panelists. For those of you online, you can put your questions into the Q&A box at any time. Please tell us your name and your institution or affiliation, and indicate if you would like us to read your question or if you'd like us to open your mic for you. We're going to do all four presentations together, and then we'll open the floor to Q&A. Thank you for coming, and I'm turning it over to our panelists now.
Great. Thank you so much. I'm Lori Glaze. I am the director of NASA's Planetary Science Division, and I'm really fortunate and excited to be here today with several members of the Juno science team who are going to be talking about some of the spacecraft's recent observations of Jupiter's moons. Galileo Galilei's discovery of these moons in 1610 marked the birth of modern astronomy. Up to that point, of course, it was assumed that Earth was the center of the universe and everything revolved around us. But when he pointed his telescope at Jupiter, what he saw there didn't fit the paradigm and couldn't be explained within that paradigm. So I thought I would show, maybe, we'll see. Go to the next one. Yes. This is perhaps a little difficult to see, but this is extracted directly from Galileo's what is it? Astronomical treatise called The Starry Messenger. And in here you can see the large circle is Jupiter, and on either side of that large circle you can see little asterisks, which are basically these smaller, what he called stars. And the movement of those stars seem to kind of go back and forth on either side of Jupiter. You'd see the little star move away, and then it would come back towards Jupiter and then perhaps disappear for a while and then maybe poke out on the other side and repeat again. And that behavior, as I said, couldn't be explained by any kind of thinking process that required revolution around Earth. But what's amazing to me is that Galileo was able to step out of his paradigm, to step out and look for alternate explanations, and realize that one explanation for that behavior was that those objects were actually revolving and orbiting around the larger object, Jupiter. And that was a major shift in how we think about our universe and how it operates. The other thing that I find interesting about this is that those observations were made in January of 1610 and published in March. So obviously they weren't following the same rigorous peer review process that we're all subject to today. But interestingly, the Juno mission, when it was moving towards Jupiter, and we'll see if we can't get this video to start. Oh, can I go back? Back? Maybe it's just delayed. You really need to see this video. It's wonderful. It's not playing. Can someone get this to play? Oh, there it goes. Excellent. So this is really interesting. So this is these are some images that were taken by the Juno spacecraft while it was on approach to Jupiter before orbit insertion. And it sort of gives you a sense of what Galileo would have seen when he was looking through his telescope. In this particular view, of course, the sun's off to the right, so you're only seeing half of the Jupiter sphere there, just the one hemisphere. But you can see those four large Galilean moons. You can see Io, the innermost moon, going around Jupiter, the next one out, Europa, then Ganymede, and kind of faintly out there, blinking in and out, is Callisto. So these, I think this is just amazing. These images were taken every 15 minutes over a period of about 17 days. And it's a pretty awesome demonstration of that same behavior that Galileo observed. Our modern observations of these moons have opened our minds to the diversity of different types of objects in our solar system. Just as Galileo's observations of these moons changed our understanding of Earth's place in the universe, the observations from the Galileo spacecraft also challenged the more modern paradigm that habitability was solely a function of how far away we are from a planet is from its star. That paradigm assumed that liquid water could only exist on the surface, that we could only have life where liquid water existed on the surface of a planet. But when we we're observing Europa using the Galileo spacecraft, and the recognition that the gravitational pull could actually drive internal energy that could sustain liquid water beneath that icy crust. We had to rethink everything we thought we knew about where life could exist. The other moons within the system are also dynamic and diverse: volcano worlds, tectonic worlds, this incredible diversity of planets that are really fascinating. And these moons are exciting destinations in their own right. This is demonstrated, of course, with the European Space Agency's Jupiter Icy Moons Explorer, which is going to launch this April, the JUICE mission, which is going to go into orbit around Ganymede and study that fascinating moon. We're going to hear a lot more about Ganymede from these speakers here today. And then, of course, NASA's Europa Clipper mission set to launch in 2024, go into orbit around Jupiter with multiple flybys of Europa to help us better understand that amazingly scientifically rich moon that could potentially harbor life beneath its icy crust. So while Juno was not really designed to explore the Jovian moons, it was designed specifically for studying Jupiter. It's demonstrated just how these future missions are going to promise to broaden and deepen our understanding of the whole Jupiter system. So with that, I want to make sure we have plenty of time for all of our speakers to share their information. I'm going to pass it over to Scott Bolton, who is the principal investigator for the Juno mission.
Well, thanks, Lori. It's great to be here. Let me see if I can move this forward. And I think we're all really excited to be able to share some of these new results that we have of the satellite flybys. As Lori said, we were designed really to study Jupiter, and it was fortuitous in our as we transitioned to our extended mission that we were able to do close flybys of the planets, and so of the moons. So what you'll hear today is I'll talk a little bit about how that orbit works and show you some early results from Europa and a little bit of Ganymede, sort of in the microwave regime. And then Tommy will show you sort of the magical fireworks that occur as Ganymede's magnetic field interacts with Jupiter's magnetic field. And then Candy will also show some great images of Ganymede and some new science from the moons as well as Jupiter. And then I'll come back and kind of do a little bit of look forward as we get ready to go by Io next year around this time. We'll get really close to that. I'll show you some images that we have of Io already that are showing how exciting that place is. Okay, so let me get started and see if it moves to the next slide there. Okay, so how is it that we actually get to go by? Let me just explain real briefly. So on let's see, this had a pointer, right? This one?
Yes.
Right here. So over here you see our primary mission. This was our first orbit. And then as the orbit evolves, Jupiter's gravity field is very strong, and it's not symmetric, it's a little oblate. And so it twists our orbit around. And so what you're seeing is that, whoops, sorry about that. Okay, so what you're seeing here is that the orbit starts here, and as it progresses through the primary mission, this is the first 34 orbits, it kind of got twisted down like this. The perijove was moving north, and where we crossed the plane of the satellites was moving inward. And this is the point where we see Ganymede. That was last summer, summer of 2021. We passed by Ganymede, and then about September 29th, just a couple months ago, we passed by Europa. So we're here somewhere right now, and we're headed toward Io. And eventually we'll get in and we'll be able to sample the rings. But the important part is this perijove is moving north. So part of our extended mission is to study the northern hemisphere really close. But it also enabled us to fly by these satellites and show you some of the results that we got today. Okay, so this is one of the new maps. So we, of course, are working closely with both Clipper and JUICE, the missions that Lori already mentioned. And this map was actually a map made by the JUICE team, who are focused on study of Ganymede. They'll also look at Jupiter, but they're going to actually go into orbit at Ganymede, and they'll launch later this year. They took our map, our images of Ganymede, and put them on the standard map of Ganymede that was made from Voyager and Galileo data. And you can see right away here the diversity. So Ganymede is an amazing world. This is a really cold place, right? So this is, even though it looks like you're looking at rock, you're actually looking at an ice shell, and it has dark terrain in it, and it has this bright terrain, and it has linear features that look like they're probably driven by tectonics. And it has these big white spots where there's craters that are producing fresh, clean ice. And so it's a very diverse place. And as I said, this is a very cold place. So this is the average temperature here is maybe about 140 Kelvin. Just for reference, Earth is about 290 Kelvin. So this is an object that's 100 degrees colder than the Earth. So it's even colder than Chicago in December. You need a lot of mittens and hats to get through this place. So you'll see more about this when Candy talks, but I want to show you what it looks like in the microwave. So one of the unique instruments that we have on Juno is a microwave radiometer. But microwaves, when you look at something in the microwave, you're generally looking at thermal emission, what scientists call black body. So the object is glowing and thermally, and we see it in the microwave. And so what you hear is 6 different frequencies in the microwave. This one is a long wavelength, so you actually see quite deep, probably tens of kilometers down. And then slowly you get toward the surface. This is getting more shallow, and then these are even more shallow. This is the highest frequency, and it's already seeing beneath the ice by several meters. And so we know that we're seeing below what's called the diurnal layer, which is when day-night comes across Ganymede, it gets warm and cold from the sunlight. We're seeing it more constant. There's a couple of main features I just want to point out here. The dark regions that I showed earlier on the visible map are very clearly related to this. We can see this. They show up warmer. The bright regions show up a little bit colder. And there's a Tross crater, which is the coldest object we looked at. That was this bright, fresh snow region. So what we're seeing when this is the first really high resolution imagery of underneath the ice. And what we can already see is the characteristics that we see at the top are going down deep. And so that's coming from layers and fracturing and different things that are going on. We're able to interrogate the ice shell. The other thing that's of interest here is that all of these are colder than we know Ganymede is. And so we're looking at the black body emission, but it's showing up colder than we know Ganymede is. And so what that means is that we're seeing reflection. Not all of the thermal emissions getting out, and there's cold sky around Ganymede that's reflecting off and coming into our microwave radiometer. And so the whole place, we see something very cold. Now that seems puzzling, but actually there's a whole bunch of information in that. And what we're seeing is that the layering, there's fracturing going on that's causing this reflection. The ice is very reflective. And as you go down deep, the different terrains reflect differently. And so that's a really interesting thing. We also are able to use this data to sort of constrain how thick the conductive ice shell is. We haven't finished all the analysis on this, but it does look like it's somewhere in the neighborhood of 50 kilometers, maybe 100 kilometers, and it may actually be varying a little bit with terrain type. So we're still in the process of analyzing all this data, but we're already able to see some thickness information. Okay, the next thing I want to show is what does Europa look like with the same microwave eyes? Very different than Ganymede. Okay, it also is an ice shell. This is even colder place than Ganymede. The average temperature is another 30 degrees colder. Again, we measure something that's even colder than we know Europa is. And so it also is reflective. In fact, it's more reflective than Ganymede. Not surprising, if you look at Europa, the ice shell is completely cracked up and you see all of these fractures in it. Those fractures are going down deep. Again, we don't know exactly how deep we are. We just got this data, but we're probably looking down tens of kilometers here and meters here. And so you go through the different layers. So one thing is there's not as much variability as you see on Ganymede. The different terrain types are not showing up quite as bright here, although there may be some correlation with something called chaos terrain. We do see those do appear a little bit different temperature and look like they're a little different. The other thing that's really important and fascinating about this is that you see some variability in all of these, but when you get to this one channel, it looks much more uniform, much more of the same color. This is what we call channel 2. It's about 1.2 gigahertz, and we're seeing down probably several kilometers. And so what would cause this? Well, one is that the ice is just more uniform for some reason down there, or you might be getting near where the global ocean is. Because if you get to the water interface, it's going to look like a mirror. Everything's going to look the same. So that's a place that we're really going to study quite a bit. Okay, so I just want to show one thing that on a Europa image, we took an image with our stellar reference unit. This is a very special camera. It's really used for navigation. And the stellar reference unit looks at stars. So it's a specialty is low light. And this is actually a picture, our highest resolution image that we got at Europa. It's about 200, 250 meters in resolution. And you're looking at the night side lit up by Jupiter shine. So it's a very innovative way to take a look at Europa and use all of our sensors. We've turned this instrument really into a science instrument, even though it was an engineering unit. And what you see is some interesting feature. This is probably a sample of what the chaos terrain looks like close up. You see a lot of cracks and roads and different things like that. And then you see this this feature here that we show. And I'll just show you real quick. This is what the image looked like before we saw it from Voyager. And then when we got a higher resolution, it looked like that. So you really are starting to learn quite a bit. Okay, with that, I'd like to pass on to Tommy, and he'll tell you about the fireworks from Ganymede's magnetic field.
All right, so Ganymede is unique in the solar system, and it has its own intrinsic magnetic field. Much like the Earth interacts with the sun, Ganymede basically is bathed by Jupiter's magnetic field and interacts with Jupiter. So I want to explain some of that to you today. So here's a graphic showing Jupiter's magnetic field lines, the big tall orange ones. And then as we will fly by along this red line, you're going to see how the magnetic field actually interacts with Ganymede. So what happens, let's see. What happens is we're moving along and you can see that it's just Jupiter out there. And then as it gets close, it begins to bend the magnetic field lines of Jupiter. And then at some point, it actually connects to Ganymede. So this is called reconnection. The magnetic field lines of Jupiter actually come along and they break apart and connect to Ganymede's magnetic field lines. And then they get peeled over the back and then they break apart again. And there's this region on the inside that are never affected by this. It's Ganymede's basically its own internal magnetic field is basically holding off Jupiter. And so it's what we call the closed field line region. And so we're going to move back. On the way out of this, I'm sorry, did I go the wrong way? Oh. On the way out, we actually measure what they call this reconnection event. We saw it in the electron populations being extremely energized, and we saw a magnetic signature. If you're looking at this image along the boundary of the closed field line, that green region, there's actually UV emissions, ultraviolet emissions. And these ultraviolet emissions are actually found just inside the boundary between those magnetic field lines connected just to Ganymede and those connected to Ganymede and Jupiter. And so they're a unique tracer, and you can get a snapshot of looking at the entire magnetic field geometry of Jupiter and Ganymede connected together by looking at the UV observations. Another observation we made was using the WAVES instrument. And the WAVES instrument measures electromagnetic radiation, so the waves passing by. And I'm going to play this little clip here for you, and it's going to be sound. We've taken the waves that were measured and put them through a speaker and actually increased the frequency such that we could hear them. And so you can actually experience what we were measuring. And the idea is that as we move closer to Ganymede along basically the time on the bottom, we get closer and closer when the densities in the ionosphere actually increase. And so the frequency increases. So we're interacting with Ganymede. As we move closer, you'll hear the pitch going. There's a lot of structure in here. It's not a very smooth distribution, and it's not symmetrical with as we flew in and as we flew out, meaning that this is a very dynamic and not symmetric ionosphere. That short little blip there, we still don't quite understand what was going on there. I mean, it's something interesting about the plasma density, and that's still under study. All right, and now I'm going to pass you off to Candy Hansen, who's going to show you some beautiful images.
Yeah, I've got a little sampler for you with Ganymede to begin with. And then I will show Europa and then Jupiter. Okay, so I'm starting with Ganymede. We are actually publishing this week a whole collection of papers in the Geophysical Research Letters. And so I just picked out one figure from the JunoCam paper to say a few things about the experience. When we were approaching Ganymede, we thought, well, the Voyager data is about the same resolution as our data, and what are we going to learn? Well, as usual, we completely underestimated what we were about to see. And with the much higher quality images, we were able to find things hiding in plain sight in the Voyager data. And so this is an example of that. Basically, these are what we call patera. They're about 50 to 100 kilometers across. They're caldera-like features. They're associated with Ganymede's bright terrain. And we believe they were part of the formation of the crust billions of years ago in a process that we call cryovolcanism, because it's ices rather than rocky lava. So we found 10 of these that were there all along. That brings the total up to about 47. And they're associated, they're in clumps on two different sides of the body. So that's telling us something about Ganymede's internal evolution. And we're trying to figure out what that clue is. That was a year and a half ago. Now we're at just the very beginning stages of looking at our Europa data. The Europa images came down on September 29th. So we've had just a bit of time to study Europa through JunoCam's images. And so this is a color composite. The resolution was about 1 kilometer per pixel. And it's the sub-Jovian hemisphere. So like our moon, Europa always keeps the same face to Jupiter. And there are not very many craters. There's one right here, and there's one up here. This lack of craters, oh, sorry, I pointed at the wrong thing. It's right there. The lack of craters tells us that this is a very young surface. And from previous data, we've known that to be the case. But there are areas on Ganymede that were not well imaged by either Galileo or Voyager. This is an example. You can kind of see the outline where it goes from kind of crispy clear to fuzzy. So we have now been able to fill in that region with the JunoCam data. And so we are able to trace the ridges and the bands. And it still looks a little fuzzy, but now we've realized that those are the ancient bands, the oldest ones on Ganymede. They're very subdued. And so you can't really see the topography as well. Over on the left-hand side is that region that Scott referred to as chaos terrain. This is also well known from the Galileo images, but we're able to map it out now more precisely in this new data. So that's just a teaser of the things to come. I know you all want to know if we saw any plumes, so I included this image. We did not. The answer is no. We were hopeful, but you know, the odds of something going off at the right time in the right place, we always knew were kind of against us. So what we've done is taken our first image and stretched the contrast so that it's very enhanced. And the place to look for plumes is along the terminator, the day-night boundary. If you see something glowing that's beyond the terminator, that's probably sticking up and still being illuminated, like the mountains in the morning before the sun rises. On the right-hand side along the bright limb, we were also looking for plumes erupting that we would see against the dark sky, and we saw none. So we've done very careful analysis of all 4 of our images, and really, truly, there's nothing. I'm so sorry. But what we did learn is that JunoCam can also image in Jupiter shine. The dark left on the left side of the image is actually Ganymede illuminated by Jupiter. So switching now to Jupiter, I'm going to show you just 3 images of the northern hemisphere, showing as we get closer how much more detail we're seeing in the clouds. This particular image was taken at 42 degrees north, and it was processed by Sergio Diaz. And it just, the colors, he did a color contrast, color enhancement that really brings out what feels to be layering in those clouds. Another one of our favorite contributors is Kevin Gill. And this is what we call by the unwieldy name of folded filamentary regions. I'd really like to come up with something else, but blob is really not very scientific. So anyway, this was taken at about 54 degrees north. And again, another example of as we get closer, we see more detail. And then finally, the northern circumpolar cyclones. We first saw these on our first Perijove pass. It was a discovery of what was going on in the polar regions. This is the North Polar, at the bottom here is the North Polar cyclone. And then surrounding it are a total of 8 circumpolar cyclones. And you can see 4 of them here. Next to between the northern circumpolar cyclones and the northern cyclone is that white storm going the other direction, an anticyclone. And we've seen this before where they sort of shove their way in and either dissipate or get pushed back out again. They don't stay. Whereas the 8 circumpolar cyclones in the north and the 5 in the south have persisted the whole duration of the Juno mission. And I'm going to end my little segment with an animation. This is as if you were flying on the Juno spacecraft. We're coming in at about 90 degrees phase angle in the northern hemisphere. And as we approach, we're going more and more north. You see those folded filamentary regions sticking out in a real 3-dimensional sense. You see those northern circumpolar cyclones coming as we pass over the pole. And then now we're going down on our Perijove pass, and things are going to speed up because we're going so quickly through Perijove. And then we get quite quickly to the equatorial zone, which is here. We just passed it. And then things slow down a bit and we make a more leisurely departure over the southern hemisphere. This time-lapse sequence was processed by Gerald Eichstadt. And you can see up in the left, there's quite a bright streak of haze just going over that cloud system there. And so with this kind of lighting, those are the sorts of things that we'll be studying in the Jovian atmosphere as we depart. We get this very unique geometry that really brings out things like the high altitude hazes. So I'm going to stop the animation there, and I am going to hand back to Scott.
Okay, I just want to show a couple of quick images of Io. So here is an image of Io. It's of the North Pole region. So Juno's in polar orbit, so we're able to see for the first time really the poles of Io. This was taken early in our mission. We were about a distance of 400,000 or 500,000 kilometers away from Io. This resolution is about 100 kilometers, but you can see the volcanic hot spots, and we've been able to monitor over the course of the primary mission over 30 orbits how this changes and evolves. And there were a couple of interesting things. The paper just came out publishing using this data that shows that there's more volcanic spots in the polar regions than the equatorial regions, which was a bit of a surprise to us. But we also see time variability. We see these things get warmer and cooler. As we get closer to Io, because next year we're going to fly by really close at 1,500 kilometers, we're getting these other images. So here's an image from about 4 orbits ago. This was a distance of about 80,000 kilometers, and the resolution is about 20 kilometers. And so you can start to see now the shapes of some of the lava flows and the calderons and things, maybe lava lakes that are existing. We're also able to identify individual volcanoes really well compared to the maps. Of course, we're seeing new ones. This is again the North Pole region. And tomorrow we fly by again. We'll get 14 more images of this. This is all taken in the infrared. And so we're watching thermal emission. And tomorrow's data will have a resolution of about 16 kilometers. So it just keeps getting better and better. And we'll be monitoring this. And it's really important as we watch the volcanoes change and get active and less active. These things are driving Jupiter's gigantic monster magnetosphere, right? So Jupiter's magnetosphere is the largest thing and largest object in the whole solar system, filled with charged particles. And this little moon is filling it with particles that are coming out of its volcanoes. And so the study of that is really going to help us. It even feeds the aurora. So it's a really important study, and we'll be doing that over the next year or two. With that, I think that's the last slide I had.
Thank you, panelists. We will open to questions now in the room and online. Just a reminder to those online, you can put your questions into the Q&A box. Please do tell us who you are and if you would like us to read your question or open the mic for you. And if you're in the room, just wave to me. I'll bring you the mic. You should also tell us who you are. Thank you. Questions in the room? Jonathan.
Thank you, Jonathan Amos, BBC News in London. Just a quick one, first of all, the resolution at 1,500 kilometers will be what, Scott, when you fly by?
I think that's getting close to about a kilometer, maybe a kilometer and a half.
Right. Yeah.
If you're on that same, in the visible light, you'll see very different.
Do you know what the highest resolution we had from previous missions of Io was? I mean, it's massively more than that, isn't it?
I think on Galileo they had some stuff that was about a kilometer, but
Did
it was
they?
only of
Right.
small territories.
Okay. Yeah.
Around Loki. Candy might know more, but I think that generally, you know, from Earth we're hundreds of kilometers, and they didn't. And so we have a lot of maps at that level.
Yeah.
We're already passing that with the 20
Yeah.
and 15 kilometer.
Yeah. And when is that? When's closest approach for that 1,500?
There's two of them, December 30th in 2023. So it's just before New Year's Eve. And then about a month later, I think it's February 3rd. We go by again at 1,500 kilometers.
Yeah. So my main question is really about JUICE and Ganymede. And I guess you've set us up nicely for the launch in April. And I was just wondering if you sort of kind of had any things that you were thinking, right, well, I know what Ganymede's got, JUICE has got. You know, what do I want to go look at in particular, having seen what I've seen with Juno?
Well, the first image I showed was actually made by the JUICE team. So they're making their plans, right? Trying to figure out what to look at with their cameras and sensors. And so they're already looking at the regions that we've identified at higher resolution than we had before and starting to make plans. It's early because they just got that image, right? But I think the microwave kind of gives you a lot of connections. So this is the first time we've really been able to interrogate the ice in 3 dimensions with a sufficient resolution to look at the different types of terrain. And so we see a connection right away, which is some people would say they expected it and some would say they're surprised. How deep does that go? What's happening? Is the fracturing different in the dark terrain, older versus the brighter, which is thought to be younger? Truss Crater was cold, really cold. So I think linking that data set, and we're still crunching through what that means with their radar data, which interrogates the ice in a different way. They're both very complementary. And so we're working closely with that team and as well as the Clipper team to figure out how they would calibrate their radars and get laboratory measurements to try to understand the impurities of the ice. There's information on the fracturing of the ice, the impurity of the ice. Is there salt? Where's the ocean? Is there liquid there? And then there's this whole magnetosphere, example. I mean, I think that's connected to JUICE as well. Everything that Tommy Greathouse presented, we have a copy of Juno's UV instrument on JUICE, and we have another copy on on Clipper. And so that team has a lot of connection to understanding the interaction between Ganymede's magnetic field, Jupiter's magnetic field, Ganymede's aurora, how does Ganymede and Europa feed Jupiter's aurora, even Io, right? We see these footprints. So I think all of that is a really rich area of collaboration. And so I think, yeah, you know, I'm probably overwhelming you because it's almost every sensor mixes together, every kind of science discipline, and they're all connected. That's one of the lessons from Juno is interdisciplinary science is really important. You know, and we used to say the magnetosphere people would study things, and then the people that are doing geology and people that are doing atmospheres were kind of separated camps. On Juno, everybody wants to be in everybody else's meeting, because as you got really close to the objects, we realized that what the magnetosphere people are seeing is connected to the atmosphere people, and the atmosphere people are connected to the interior. So nobody wants to miss anything. And I think that's kind of a change for all of space science, is as we progress from the Voyager era of flybys to the really close-up stuff, the science disciplines are merging, which is kind of cool.
Will be online.
We just have a quick clarification. Have the images you shared today been released previously?
Well, JunoCam is an outreach instrument. So everything I showed is actually on our website. The images get processed by citizen scientists and posted back on our portal. The only one that is not on the portal right now is that close-up that I showed of Europa from the new images, and that is being released today.
Any further questions in the room? Online?
Yes, we have a question from Rebecca Sohn for space.com. Candace mentioned that you did not see any plumes. Are there any other opportunities to observe these plumes for Juno or maybe for JUICE?
Well, certainly for JUICE. For Juno, we're not going to get close again. If you study the graphic that Scott showed, we have now passed Europa and we're headed in closer and closer to Jupiter. So we won't get close again. If we have any opportunities from a distance, of course, we'll use them. But I think we do not. So this was it, really.
Yeah, Jonathan Amos again. Can you just tell us where you are with the mission? I mean, when we launched, God, I remember you're sitting up there at Mars Sample, not Mars Sample, but was it Curiosity? I can't remember, wasn't it? We were all at Kennedy.
MSL, I think.
Yeah.
Yeah.
Geez, that's a long time ago, isn't it?
I'm old.
We all, yeah. But I mean, we were talking about the radiation environment at Jupiter and the challenge that presented to you. Solar panels, solar wings, because
Right.
obviously, you know, you're not a radioactive battery mission. I mean, how is Juno doing? It's been living out there for quite a while now in very challenging circumstances.
Yeah, it is. It's actually really healthy. I mean, we don't see you know, any real degradation due to the radiation. I mean, you know, we're built like an armored tank, and the shields are holding. And we do go through, you know, really hazardous regions, right? And we've been able to do that and monitor that a little bit, but we don't see advanced degradation on the solar arrays. We don't see any electronics or sensors. I mean, we have big vaults and radiation protection. And in some sense, JUICE and Clipper are modeled after what how we designed as well. So hopefully they will share the same kind of success that we have. And we've been around longer than we anticipated, right? Again, the orbit though is really, you gather your radiation per orbit. And so we're, I think, going on our 47th orbit now. So we were designed for 34 with some margin. And I don't think we're running into problems yet, but I do want to caution, you know, I'm very optimistic, but we go through a more severe radiation region with each orbit. We're designed that way. So it only gets worse, but we're doing great, as you point out. And we already passed Europa and we're headed to Io, which is just amazing. And when you get close to Io, you're in the middle of some really bad stuff.
But for the time being, you have to keep on asking Laurie for more money. I mean, what's
Um,
the,
I'm going to let her take that.
Speak to that, Jonathan. So the Juno mission underwent its senior review for extended mission. That was in 2019. I can't remember what year it was. And we actually at that time recognized that this opportunity existed to allow the orbit to keep progressing as it is. It enables these observations of the Jovian moons, which is great. But we also recognize that that's going to be an increasingly more challenging radiation environment. So what we did when we approved the extended mission was to basically say you're approved until the spacecraft can no longer operate. And we recognize that that's probably going to happen, I don't know, you can give the time. I won't speculate on the time, but it ultimately it will, I'm sure, succumb to the radiation. So we've already agreed to fund and support the mission until it gets to that point. I don't think that's going to be, hopefully it's not a very long-term commitment. I mean, we want to keep getting the science as much as we can get out of it. That's really the point.
and you don't have to do an active disposal. I mean, you're not worried about crashing into Europa.
We were talking about that yesterday.
So the original plan was to do an active disposal in order to make sure we didn't crash into Europa, right? And planetary protection is what it's called. And we were able to carry that plan. And then we also realized that in the extended mission, once we passed Europa, it was nearly, or is impossible to actually get back there. I mean, even if we fired every rocket engine and used everything we had, and when we're not doing that, we don't have enough to go back, right? Jupiter's gravity field is much more powerful than our mere mortal engines. And so the idea is that once we pass that, there's no way to crash into Europa by accident. And if you just let it go, Juno will eventually go into Jupiter by itself. And so that's the plan we've outlined and proposed. It's going through a various process for approval and analysis, but I think that it looks like that's the easiest route to follow. And I will point out that, the end could come in two different ways. You could have a degradation of the radiation. And if you keep surviving the radiation, eventually we're going to run out of propellant. And what we use the propellant for is making minor modifications to the orbits. But more importantly, that's how we steer and point our high gain antenna to go to the Earth and point our solar arrays to the sun. And so once you lose that capability, you may be healthy moving around. You could even be collecting data, but you can't send it back. And I doubt that the funding will continue to flow under those circumstances.
If we're not getting the data, probably
Right.
not.
So at the end, it's going to be one of those two.
Do we have any further questions in the room? Going once, going twice, online? That we'd like to thank our speakers and close this session. This recording of this session will be available this afternoon on AGU's YouTube channel. We'll make that available to reporters on the Press Information Exchange, along with, I think we have the videos and the slides from the speakers. Our afternoon session is wetland losses and record methane increases. And at 2 p.m., reviving wild rice through Indigenous Centered Collaborative Research. So we hope to see you there. Those are roundtable events, so they'll be in the room across the hall, 231, or online following the Zoom links. If you're interested in more space, tomorrow at 1 p.m., Pioneering Planetary Events, what comes next after DART's asteroid impact. And on Friday morning, one more session, first sample depot on Mars, next science campaigns for NASA's Perseverance rover. So we hope to see you there too. Thank you, speakers, again. Thanks for coming.